Welcome to Chapter 7, Part 1, Normal Probability Distribution. Section 7.1, Properties of the Normal Distribution. Because an infinite number of outcomes are possible for continuous random variables, the probability of observing one particular value is zero. For example, the probability that your friend is exactly 12.9438823 minutes late is zero. This result is based on the fact that classical probability is found by dividing the number of ways an event can occur by the total number of possibilities. There is one way to observe 12.9438823, and there are infinitely number of possible values between 0 and 30. To resolve this problem, probabilities of continuous random variables are computed over an interval of values. For example, we might compute the probability that your friend is between 10 and 15 minutes late. To find probabilities for continuous random variables, we use a probability density function. A probability density function, or PDF, is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. The first one being the total area under the graph of the equation over all possible values of the random variable must equal 1, meaning the total area must equal 1. This is similar to the discrete probability distribution, where the probability must also equal 1. Number 2, the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. So the curve cannot fall below the x-axis, and it is approaching 0 to the left and to the right of the curve. This is also similar to probabilities, where the probabilities must be greater or equal to 0. So because the total area under the density curve is equal to 1, there is a correspondence between area and probability. The area under the curve equals probability. So if you see or hear under the curve or probability, they mean the same thing. So to find probabilities for continuous random variables, we do not use probability distribution functions as we did for discrete random variables. Instead, we use probability density functions. So the word density here is used because it refers to the number of individuals per unit of area. So objective 2, graph a normal curve. So not all continuous random variables follow the uniform probability distribution. Some continuous random variables, such as birth weights or IQ scores, follow a bell-shaped distribution. So consider the following histograms. Notice as the class width decreases, the red curve closely approximates the histogram. The red curve is a model called the normal curve. So if a continuous random variable is normally distributed or has a normal probability distribution, then a relative frequency histogram of the random variable has the shape of a normal curve, or it's bell-shaped and symmetric. Okay? So if we look at these histograms here, as we increase the number of units, so the number of intervals, the rectangles, we get closer and closer to a bell-shaped curve, or in this case, because we're dealing with continuous variables, the normal curve. And the normal curve will take the shape of a bell-shaped curve. All right, so this is an example of the normal curve. Okay, so we have an image here that takes the shape of a bell-shaped curve that is symmetric. So mu is our center. Okay, the value that is represented here by the mean is going to be also the mode. Okay, because the mode is going to represent the high point of the graph. All right, in our distribution. 50% of the data will be to the left and 50% of the data will be to the right. Okay. These points here are going to be our inflection points. This is where the graph changes. Okay. All right. So this is where the graph, where you can say the curve changes. And of course, we have our standard deviation where we're increasing by 1 standard deviation, then 2, then 3 to the right, and then decreasing by 1, then 2, then 3 to the left. Notice too that the bell curves are approaching 0 when they are increasing and decreasing. So let's determine whether the graph can represent a normal curve. If it cannot, we need to explain why. So for number 6 here, this would be a representation of a normal density function. All right, we have a normal curve here, which is representative of a bell-shaped curve. It is also symmetric, and our curve is approaching 0 as we are increasing and decreasing x. 8 would not be a representation of a normal curve because the graph cannot represent a normal density function because it does not approach the horizontal axis as x is increasing and decreasing. So the ends of our normal curve are now curving up. Okay, so that's not taking the shape of a normal curve. And then for number 10, this also does not represent a normal curve. Here, the graph cannot represent the normal density function because it is not bell-shaped. Although our graph is decreasing or approaching the horizontal axis as x increases and decreases, we have 2 modes in this curve, making it not bell-shaped. All right, for our next 2 examples, the graph of a normal curve is given. And now we want to use the graph to identify the values of mu and sigma. So in other words, we want to find the mean and the standard deviation when given the normal curve. So on the first one here, notice that our line of symmetry, which is right in the middle here, all right, this line right here, is given by the value 5. So that means our mean is going to be 5. Okay. Now we have values to the right and to the left of 5, and we know that we would be increasing and decreasing by the standard deviation. So in order to find the standard deviation, we're going to need to determine the difference or the distance between each number. And that's going to be the value 2. So we're increasing by 2 to the right, and we're decreasing by 2 to the left, making our standard deviation sigma 2. So mu is 5 and sigma is 2. For our next one, our line of symmetry here is going to be 530. So now to determine the standard deviation, we are going to subtract either 530 from 630, or we'll take 530 minus 430 to find our standard deviation, which is 100. Okay. Objective 3, state the properties of the normal curve. So the normal probability density function satisfies all the requirements of probability distributions. So here are the properties that we need to keep in mind. So 1, the normal curve is symmetric about the mean. That means the mean is going to be our line of symmetry. So because the mean equals the median, which equals the mode, the normal curve has a single peak, and the highest point occurs when x equals the mean, mu. So the normal curve has inflection points which occur at mu minus sigma and mu plus sigma. So 1 standard deviation to the left and right of the mean. The total area under the normal curve is 1. Half of the area is to the right of the mean and half of the area is to the left of the mean. So as x increases without bound, meaning it's getting larger and larger, the graph is going to approach but never reaches or never crosses the horizontal axis. Similarly, as x decreases without bound, meaning it's getting more and more negative, the graph approaches but never reaches, never crosses the horizontal axis. And then the shape of the curve is affected by two things, the population mean and the population standard deviation. So that's mu and sigma. Now, just like in the probability distributions we've looked at previously with normal distributions, the empirical rule applies. So approximately 68% of the area under the curve is going to be within one standard deviation of the mean. Approximately 95% of the area under the curve is going to be within two standard deviations of the mean. And then approximately 99.7% of the area under the curve is going to be within three standard deviations of the mean. So remember that the area under the curve, when you see that phrase, means the probability of X occurring. Okay, so the area is the same thing as probability. It's the same thing as proportion, which then also gives us the percentage and the percentile. Okay, so all those words are interchangeable with each other. So in this example, we're asked to draw a normal curve and then label the mean and inflection points. Remember, inflection points are going to be the one standard deviations to the left and right of the mean. So in this problem, we have a mean of 50 and a standard deviation of 5. So when we draw our normal curve, it's going to have the shape of a bell-shaped symmetric curve. Our mean is 50, so that means our line of symmetry right in the middle is going to be labeled 50. And then we need to label our inflection points, which are going to be one standard deviation to the left and one standard deviation to the right. Since our standard deviation is 5, we are going to increase 5 to the right and then decrease by 5 to the left, giving us the values 45 and 55 for our inflection points. Objective 4, explain the role of area in the normal density function. So the normal curve is a mathematical model, like an equation, a table, or graph that is used to describe reality. The normal curve does a good job of describing the distribution of things like height, IQ scores, birth weights, etc. So suppose that a random variable x is normally distributed with a mean mu and a standard deviation sigma. The area under the normal curve for any interval of values of the random variable x is going to represent either the proportion of the population with the characteristic described by the interval of values, or the probability that a randomly selected individual from the population will have the characteristic described by the interval values. So in our first practice problem here, we are told that the distance in feet a home run traveled in 2017 approximately normally distributed with a mean of 400.3 feet and a standard deviation of 25.6 feet. A is asking us first to draw a normal curve with the parameters labeled. So we know that this is normally distributed, which means it's going to take on the normal curve. So we're going to draw our bell-shaped curve. We also know that our mean, which is our line of symmetry, is 400.3. And then we know our standard deviation, which is 25.6. So we're going to be increasing our value to the right by 25.6 and then decreasing by 25.6 to the left. All right, so here I've drawn my bell-shaped curve. I've identified where my mean is as well as my checkpoints for my standard deviation. So since my mean is 400.3, I'm just going to increase by 25.6 to the right and then decrease by 25.6 to the left, going all the way out to 3 standard deviations. B. B says to shade the area under the normal curve to the right of x equals 450 feet. Now I have my scale right here and I need to now locate where 450 feet will be. So at 2 standard deviations to the right of the mean, I have 451.5. So 450 is going to be a little bit to the left of this check mark. So when I draw this normal curve, I'm going to label x equals 450 to the right. Feel free to identify this on the same graph. I just showed here 2 different graphs so you can see how I got the normal curve visual here for B. I labeled it x equals 450, and my directions tells me to shade the area under this normal curve to the right of this value. So I then shaded here on the right-hand side. So C is saying, suppose now that the area under the normal curve to the right of x equals 450 is 0.026. So this shaded area, all right, has a total area of 0.026. We need to now provide 2 interpretations of this result. So this is asking us, or sorry, not asking us, telling us that the probability, let me go back to my visual, the probability of x greater than 450 is going to be 0.026. So that means that the proportion of home runs that traveled a distance greater than 450 feet is 0.026, or that the percentage of home runs that traveled a distance greater than 450 feet is 2.6%. Both of them mean the same thing because area means probability, it means proportion, and it means percentage and percentile. Okay, so D, among all the home runs hit, what proportion exceeded 450 feet? Well, the proportion of home runs that exceeded 450 feet is 0.026 or 2.6%. All right, let's do another example. So here our problem tells us that the heights of 10-year-old males are normally distributed with a mean of 55.9 inches and a standard deviation of 5.7 inches. A asks us first to draw a normal curve with the parameters labeled. So this is similar to the last problem here. We're asked to draw a normal curve. Since it is normally distributed, it's going to take on the shape of a bell-shaped curve. We know the mean is 55.9, so that means my line of symmetry right down the middle of my bell-shaped curve is going to be labeled 55.9. The standard deviation is 5.7, so I'm going to be increasing those values to the right by 5.7 and then decreasing by 5.7 to the left. So now that I have my checkpoints for each of the standard deviations, I can now continue on to B. So B tells us to shade the region that represents the proportion of 10-year-old males who are less than 44.5 inches tall. Okay, so we need to identify where 44.5 is going to be on our bell-shaped curve. So 44.5 is an actual checkpoint value. It is the value for 2 standard deviations to the left of the mean. So when I identify that, I can now label it x equals 44.5 and then shade to the left of that value. So that means that my shaded region is going to be the probability that x is less than 44.5. So C then tells me that suppose that area under the normal curve to the left of 44.5 is 0.0228. Provide 2 interpretations of this result. Well, the first interpretation is going to be that the proportion of 10-year-old males who are less than 44.5 inches tall is 0.0228. And another interpretation of this value is going to be that the percentage of 10-year-old males who are less than 44.5 inches tall is 2.28%. Okay. Alrighty. All right, so next here we have a practice. So I encourage you to pause this presentation, attempt the problem, and then come back. All right, so I hope you attempted the problem. Here we are asked that the birth weights of, well, we're told that the birth weights of full-term babies are normally distributed with a mean of 3,400 grams and a standard deviation of 505 grams. A asks you to draw a normal curve with the parameters labeled. So you should have drawn your bell-shaped curve, identified your standard deviations to the left and to the right of the mean using the standard deviation unit 505 grams. B then tells you to shade the region that represents the proportion of full-term babies who weigh more than 4,410 grams. So 4,410 grams happens to be 2 standard deviations to the right of the mean. So we would label that and then shade the region to the right, because the right values are the values where full-term babies weigh more than 4,410 grams. So C then tells us that suppose the area under the normal curve to the right of 4,410 grams is 0.0228. Provide 2 interpretations of this result. So our 2 interpretations are going to be that the proportion is 0.0228, that the birth weight of a randomly chosen full-term baby is at least 4,410 grams, or 2.28% of all full-term babies have a birth weight of at least 4,410 grams. All right. Go ahead and do one more practice problem for this section. Pause the video, attempt the problem, and then come on back. So hopefully you paused and you attempted the problem. So this problem tells us that the Graduate Record Examination, or the GRE, is a test required for admission to many U.S. graduate schools. Students' scores on the quantitative portion of the GRE follow a normal distribution with a mean of 150 and a standard deviation of 8.8. In addition to other qualifications, a score of at least 152 is required for admission to a particular graduate school. You are asked to draw a normal curve with the parameters labeled. So since we know our normal curve is normally distributed, we can draw our bell-shaped curve, identify our mean, which is our line of symmetry at 150, and then our standard deviation is 8.8. So we would find the standard deviations 1, 2, and 3 to the left and right of our mean by adding and subtracting 8.8. B then says to shade the region under the normal curve that represents test takers who scored above 152 on the verbal portion of the GRE. Now, 152 lies between the mean and our first standard deviation to the right, but it is more located to the value 150 than it is to 158. So we would draw a line closer to 150 to identify where 152 is located. Now we want to shade values that are above 152. So once we've drawn that line for 152, we would then shade everything under the normal curve to the right of that line, as you see here. So this shaded region then represents all of the values that are greater than 152. Okay. Now C tells us that this area that we have now just shaded is 0.4090. And we now need to provide 2 interpretations of this area. So the first interpretation is going to be that the proportion of students who score above 152 on the verbal portion of the GRE is 0.4090. The second interpretation could be that the probability that a randomly selected student will score above 152 on the verbal portion of the GRE is 0.4090 or 40.9%. All right, and that concludes section 7.1.